Hi everyone, I will be presenting today is about enabling distributed DNNs for the mobile web over cloud edge and end device. And the contents include the overview of executing DNNs on the web, two ways for accelerating DNNs for the web with edge computing and some thinking and discussion. For slide 3, as we all know, deep neural networks as a representative way of achieving artificial intelligence in numerous applications also show great promise in providing more intelligence to the web applications. So as shown in the figure, there are two typical DNS execution schemes on the web. The first approach is executing the whole DNS on the web via JavaScript and WebAssembly, such as TensorFlow.js, Petals.js, and Keras.js, WebDNN, etc. So, however, this approach requires a high transmission delay for loading heavy DNN models. For example, TensorFlow.js ResNet 50 deep learning model whose size can be up to 97.8 megabytes. So besides the limited computing resource of the web, also performs a slow inference, even we can accelerate computation by WebAssembly or Web GPU. And more commonly, the cloud-only approach offloads the whole task by executing the whole DNNs on the remote cloud. Thus, large amounts of data such as images, audios, and videos are sent to the remote cloud, and it increases the computing pressure, especially for high concurrent requests. In addition, transmitting the complete task to the remote cloud also raises new privacy concerns for users, such as home security cameras. Slide 4. As mobile edge computing is becoming an important computing infrastructure in 5G era, it's promising to consider the use of the edge cloud that has the benefit of low communication costs compared to offloading computations to the remote cloud and relieves the burdens of the core network too. So to accelerate distributed DNNs for the web, it's natural to consider the use of partition offloading approach to leverage computing resources of the end devices in the edge server. So notice that we can deploy the web applications on the edge server, and remote cloud is responsible for training DNN models with GPUs. This approach partitions the DNN's computation by layers and dynamically distributes the computations between the web and the edge server, since the mobile web loads just a small portion of DNN models and access a part of DNN computations. So we can protect the data privacy by transmitting the intermediate results to the edge server for executing the rest of the inference instead of transmitting the whole tasks. So, however, the challenge is how to provide dynamic DNN partition to cope with various tasks, unstable network conditions, and various devices with different computing capability. So how can the web or mobile web perceive and measure the computing capability of the device and monitor the network condition when employing partition offloading approach into the web? As for slide 5, with partition offloading approach in edge computing infrastructure, although a small portion of DNN computations can be offloaded to the web, the edge server still has to undertake the majority of DNN computations. So we introduced adding an efficient branch to the traditional DNNs for executing inference on the web independently. Concretely, we add a binary neural network branch at the first convolutional layer of the traditional neural network, and it has the same structure to the rest of the traditional neural network. Thus, it's easy to design a lightweight DNN for the web, especially for the mobile web, without rich expert experience and knowledge. So, which also can provide accurate compensation for the lightweight branch via collaborative mechanism. For a given sample, if the binary branch is confident to predict the result and satisfy the users, the sample can exit from the binary branch directly. Otherwise, it has to transfer the output of the first convolutional layer to the edge server for a precise result. And mirroring the confidence of inference results can use the normalized entropy, which is always employed in collaborative DNNs. And then we compare the normalized entropy against a threshold to determine whether or not exit from the tiny branch. We pick the appropriate value by then exit from a threshold as a hyperparameter during the training phase. So in summary, adding lightweight branch can reduce the model size and accelerate inference on the web, which provides a collaborative mechanism with the edge server for accuracy compensation. So, okay, slide 6. Furthermore, we also consider that in actual scenarios, user requirements for delay, network conditions, and the computing capabilities of device may change dynamically. So, as a constant lightweight branch or traditional DNN compression network cannot meet the requirements. So thus, this requires providing a context-aware pruning algorithm that incorporates the latency of the network condition and the computing capability of the device. And in this figure, we show a deep adapt framework across the mobile web, the edge server, and the cloud server, which contains offline and online phase. And the offline phase consists of network pruning, model cache updating, and deep adapt employs a context-aware runtime adapter, providing a pruned model that will be optimal for the mobile user by monitoring the network condition and incorporating the CPU frequency of the mobile device. So, when this proved model is unsatisfactory for the mobile user, so deep adapt then receives output from the first convolution layer for the mobile web from the mobile web and receives output from the first convolution and executes the rest of the inference of the unproved model on the edge server. So for each new request result merged to the model, we first leverage the edge server to process the mobile user's request, and then we send the pruning requirement to a message rest queue of network pruning modular on the cloud server. And the network pruning modular obtains the requirements from the request queue, then proves the network and updates the pruned model to the model cache of the edge server for the next similar request. Okay. And slide 7. Although we have discussed some ideas for accelerating the execution of DNNs on the web to implement AI service, they still face problems in actual deployment. The first thing is what role should the edge server play in providing processing support for intelligent web applications requiring heavy computation? So I mean, is there a better computing collaboration or deployment model for accelerated DNN? The second is how to developers use the edge server more easily for accelerated DNNs and collaborating with web apps. And the third thing is how can the edge server deploy and offload DNN computations more easily, including how web apps can monitor changes in network conditions and response to the edge server, and how the edge server can perceive the computing capability of the device and distribute appropriate computation to web apps for execution in real time. Okay, this is what I want to share and discuss about how enabling distributed DNNs for the mobile web over cloud, edge, and device. And thanks for your lesson.